All right, let's dive into a real chemical mystery. And I mean a real one, the kind that your basic high school chemistry class probably couldn't explain. And it all revolves around something you're doing right now: breathing. Yep, the oxygen molecule. It's got this hidden secret, and unlocking it is going to give us this amazing new lens to see all molecules. It's called molecular orbital theory. So, where does this mystery begin? Well, it's not with some complicated formula or abstract concept. Nope. It starts with a simple, kind of weird observation that seems to break all the rules we thought we knew. Yep, you're seeing that right. When you cool oxygen gas way, way down, we're talking negative 183 degrees Celsius, it turns into this really pretty pale blue liquid. But here's the crazy part. If you pour that liquid between the poles of a super strong magnet, it doesn't just fall through. No way. It actually gets stuck. It just hangs there, trapped by the magnetic field. And that is the million-dollar question. Because honestly, based on how we're first taught to draw molecules, this should be completely impossible. It just shouldn't happen. Okay, so this right here is where things get weird. On one side, you've got the good old Lewis structure for O2. You probably remember this from chemistry class, right? Look closely. See how every single electron has a partner? They're all paired up. And in the world of magnetism, paired electrons basically cancel each other out. So this model is shouting at us, hey, oxygen is not magnetic. But then you look at reality, and the reality is it absolutely is magnetic. Total contradiction. So what does this tell us? It tells us our simple model, the Lewis structure, is useful for some things, but it's missing a huge piece of the puzzle. The map we're using is just wrong. We need a better map. And that new, better map is exactly what we're talking about today: molecular orbital theory, or MO theory for short. It's a much more powerful way of looking at what electrons are actually doing inside molecules, and it's the key to cracking this whole case wide open. Now, to get this, we have to make a pretty big mental shift. You have to kind of forget the idea that electrons belong to one specific atom. MO theory says that once atoms bond, their electrons get communal. They belong to the entire molecule, not just their original home atom. It's a wild idea, but it's way closer to the truth. So, if these electrons are living in the molecule as a whole, they need new places to live, right? We call these new places molecular orbitals. The best way to think about it is like this. When two atoms decide to move in together, they don't just keep their separate apartments. They pool their resources and build a brand new house, a molecular house, with all new rooms for the electrons. So how exactly does this whole molecular construction project work? Luckily, it's not random. There's a set of rules, a logical system for how these new molecular homes get built. It's actually pretty straightforward. You start with your two separate atoms. You bring them close enough that their original orbitals, their atomic orbitals, start to overlap. And here's the key rule. For every two atomic orbitals you mix together, you get two new molecular orbitals out. But, and this is a big but, they're not the same. So, those two new orbitals are very different. One is called a bonding orbital. Think of it as the stable, low-energy basement apartment. Electrons here are happy, and they act like glue, holding the molecule together. The other one is an anti-bonding orbital. This is the unstable, high-energy attic. Electrons up here are antsy, and they actually push the atoms apart, weakening the bond. Now that we've built our new molecular house with all its different rooms, how do the electrons move in? Simple. They're lazy. They always take the easiest, lowest energy spot available first. It's like pouring water into a glass. It fills from the bottom up. Same idea. Okay, we've got our new way of thinking. We've got our rules. It is time. Let's go back to our original mystery and apply this powerful new tool to the oxygen molecule and see what happens. This is the big reveal. So here's the game plan. We're going to take two oxygen atoms. We'll merge their atomic orbitals to build our brand new molecular orbital diagram. Then we take all their valence electrons. That's 12 in total, 6 from each. And we start filling in the diagram, always starting from the bottom, the lowest energy level, and working our way up. So we start filling it up. The first orbital gets 2 electrons. They pair up. The next one gets 2. They pair up. It's all going according to plan. But then we get to the very last 2 electrons. And we hit a snag. We have 2 orbitals that are at the exact same energy level. What happens? Well, think about getting on an empty bus. You don't sit right next to a stranger if there's an open seat, right? Electrons are the same way. They want their own space if they can get it. And that one little preference, it changes everything. And there it is. The answer. The MO diagram for oxygen shows clear as day that those last two electrons do not pair up. They each take their own orbital at that energy level. The result? Our oxygen molecule is walking around with exactly two unpaired electrons. And those are our culprits. You see, an unpaired electron, because of this quantum property called spin, acts like a tiny little magnet. So when you have a whole bunch of molecules that each have these tiny magnets inside them, and you put them in a big magnetic field, they all line up, and the whole substance gets pulled toward the magnet. Mystery solved. MO theory didn't just stumble upon the answer, it predicted it perfectly. So, okay, we cracked the code for oxygen. That's cool. But the real reason MO theory is so important isn't just about solving weird little puzzles. It's about what this theory lets us do, what it lets us predict, and even better, what it lets us design. I mean, look at this list. By building one of these diagrams, a scientist can figure out all sorts of things about a molecule before ever making it in a lab. Is it even going to be stable enough to exist? How strong will its bonds be? Will it be magnetic? What color will it be? Can it conduct electricity? MO theory gives us a shockingly accurate sneak peek. You know, that's really the best way to think about it. A simple model like a Lewis structure is like a sketch of a house that's already built. But MO theory is the actual architect's blueprint. It tells you how the house is going to stand, what its properties will be, and how it will behave before you even lay the foundation. And that really is what's so exciting. It leaves us with this incredible question. Now that we have the power to read the actual blueprints of molecules, what can we build? What new medicines, new materials for technology? What new solutions can we engineer now that we understand the fundamental rules? The possibilities are pretty amazing to think about.